To simplify the calculation of amplitude in quantum field theory, Feynman introduced some rules. Many of these rules are common to all theory, meaning to all starting Lagrangian. However, some of the rules depend on the Lagrangian itself, and in particular its interaction part. So we are going to give here the Feynman rules for the 5-4 theory we have been using so far. The first rule is that we should draw diagrams for the process we are interested in. So for instance, in a collision, we have two incoming lines and two outgoing lines. And these diagrams are made of vertices, that's a dot here, connecting four lines. And that's because we are in the 5-4 theory. We have four fields interacting at some given point of space-time. The second rule is that each line should be labeled by its associated 4 momentum k, and for the calculation of the amplitude we associate a propagator in momentum space for each of these lines. The third rule is that to each vertex we associate the value minus I lambda times delta function, which ensure that we have conservation of energy momentum at each vertex. The fourth rule is that we integrate over the momenta of internal lines. So an internal line is a line connecting two vertices, so that's at least in second order in lambda. In first order in lambda we don't have such internal lines. And the final amplitude should only depend on the initial and final momenta for the process we are interested in. It should not depend on the internal momenta, and that's why in quantum mechanics we have to sum for the amplitude associated to each possibility, and therefore we have to sum over each momentum for internal lines. The fifth rule is that some diagrams have a symmetry factor S, and that happens when we have different ways to connecting internal lines together to the vertices. The sixth rule is that we have no propagator for external lines, and that's because the external lines are only here to bring the particles to the collision point or the interaction, and they are not part of the interaction itself. And usually when, for instance, we are interested in a collision process, we don't take into account the external lines. The last rule is that we do not write explicitly the delta function ensuring the global conservation of energy momenta between the incoming and the outgoing lines. However, we assume it's always there, and that means that we are only calculating processes which conserve energy momentum between these incoming and outgoing lines. That's something you should check always before going to the calculation and application of the rules. So let's take as an example the collision of two particles in the first order in lambda. According to rule 3, the vertex is proportional to lambda. Therefore, we only keep diagrams which have only one vertex. Only the first diagram corresponds to a collision between the particles. The other two correspond to different processes, like the interaction with the vacuum and the vacuum fluctuation itself. The second rule tells us to associate a k with each line. So these are given by the incoming and outgoing for momenta. We have k1, k2, k3, k4. And we should in principle also associate a propagator for each of these lines. But according to rule number 6, we have no propagator for external lines. So we don't need to incorporate any propagator here, and that's because we have no internal line. Now, according to rule number 3, we also need to associate minus I lambda 2 pi 4 and a delta function for ensuring energy momentum conservation at each vertex, but we have only one vertex, and according to the 7th rule, we see that we don't need to write explicitly the global energy momentum conservation. Therefore, we don't need this factor, and we only have minus I lambda to take into account. Rule number 4 tells us that we should sum over momentum for internal lines, but we have no internal line in this diagram. Rule number 5 tells us that there should be a symmetry factor that's associated to the different way to connect the internal lines to the vertices, but here there is no internal line again, therefore the symmetry factor is just 1. Then we recover the amplitude for the collision in first order in lambda, which we obtained before. We can use the same rules to get the second order in lambda. In this case, we will have 2 vertices, and therefore there will be internal line to sum over, and also symmetry factors associated to them.